Chapter 5, Number 4. You are pulling your little sister on her sled across an icy, therefore frictionless, surface. It just means the ice doesn't pull back on the sled in any way. When you exert a constant horizontal force of 120 newtons, the sled has an acceleration of 2.5 meters per second squared. If the sled has a mass of 7.4 kilograms, what is the mass of your little sister? There are a couple of bold assumptions in here, which are fine, I suppose, but it's important to recognize. Let's draw a picture, and then we have the sled, which looks like that, let's say, and on the sled is your little sister, and then out here somewhere is you, and you're pulling the sled. A couple of things. It's not clear if the ice is frictionless how you are moving across it, and we're basically assume that should be ignored. Well, maybe you have cleats so that for you, you dig into the ice and it's not frictionless or whatever. Don't worry about it. Somehow you are able to exert this 120 Newton force, and the sled therefore accelerates. The other thing we're going to do is treat the sled and the sister as one object, which really isn't justified here. If you yanked really, really hard, then the sled would pull out from under your sister and she'd fall off the back and you'd get in trouble with your parents or whatever. But we're going to treat them as if they were one object. So we just have an object, and we say what forces act on that object. So we definitely have that the person is pulling this way, and we have that the object accelerates this way. So that's our free body diagram. Technically speaking, we have two other forces that I'm going to put in yellow so they're hard to see. We definitely have that the sled is being pulled down by the earth, which is a force usually called Fg, but then that's going to be resisted by the ice, so she doesn't go through the ice, and we know that in the end those two forces will happen to cancel out in this case. It's really a little early for Walker to have thrown this problem out here. If you thought about that, and I always love where problems are like they work because you don't think about what makes them not work, but we'll talk about this more in class in the second half and find out that there is a force pulling down from the earth, but there's a force from the ground pushing back up, and they'll exactly cancel. So horizontally, the motion we assume is horizontal, and the only horizontal force is Fp. So we can say that the net force in the horizontal direction from the diagram is Fp, which we know to be 120 newtons. And then here, our sled plus sister has a total mass, we'll say, called m. And we know that from second law that right now this is not from the diagram, this is from Newton's second law, that the sum of forces in the x direction will be the mass times the acceleration in the x direction, and we have that as well. So it's the mass, the total mass, times 2.5 meters per second squared. And then we have, of course, that anything is equal to itself. So we can say that Fp is the total mass times the acceleration, and therefore 120 newtons is the total mass times 2.5 meters per second square. So the total mass is 120 newtons over 2.5 meters per second square. Quick check, the units work out, that's nice. And we get 120 over 2.5, or 48 kilograms. But, and this is the important bit, that the total mass, and I keep stressing the word the total mass, is the mass of the sled plus the mass of your sister. So we have that 48 kilograms is the mass of the sled, 7.4, plus the thing we wanted, the mass of your sister. So we can solve that to get that the mass of your sister is 40.6 kilograms. And this really does assume that your sister and the object and the sled are one object. And later in the class, probably next chapter, we'll talk about what if that isn't treated that way, and can we still get the right answer? And the answer will be yes. All right.